So let's summarize what we know, all right? And I copied these right out of the book because I didn't want to LaTeX it all, but right, this K, it's, region 1, A, E, I, K, X plus B, E, negative I, K, X. Here, they're saying K, H bar is the root 2M, E, K, right, where the EK, that's the kinetic energy, the initial kinetic energy this particle has. Right, I can write that also as 2M, EK over H bar squared, all square root, right? So that's the same form that we came up with, okay? Similarly, right here, we use the letter kappa for region 2, and that's, I could write that as 2m v minus e over h bar squared, all square root. And then we recognize this k right here is 2me over h bar squared square root, where now this e will be different than this ek. Okay? So what do we need to do now? Well, we need to normalize all three of these solutions simultaneously to solve these boundary conditions. And it's a mess. It's a total mess. And I'm not going to require you to go through and do it all. I am going to set it up. And what I will say on this Mathematica 4 assignment that I've got here in front of me, there will be a bonus opportunity at the end of this for you to be able to create this plot that I've created right here. And we can only create this plot right here by being able to normalize all of these simultaneously. Okay, so let's just set it up. All right. So one thing we need to recognize is we need to normalize all three of these functions together such that their values are single valued, right? So in other words, if you look at, this wave function in region 1, it's just got to smoothly transmit right through region 2. And then similarly, the region 2 solution has to smoothly transmit through region 3. So that's just one of the requirements of wave functions, right? That they have to be single valued. Another requirement is that it has to be continuous. So you can see here, this is showing you the slope, this blue line that I'll dot right there. That's showing you that the first derivatives across those solutions have to be continuous, okay? So if we look now, summarizing these three regions, what do I have right here? Okay, great. So let's build up these solutions. So the first thing we note is the values of psi have to be all equal to each other, okay? And so I'm going to define this in my picture here. I'm going to call this border the first place of the barrier, x equals 0, and I'm going to call this boundary x equals L, okay? And so what this means now, let's see. So in my region 1 solution, which I'm going to write A, E, I, K, X plus B, E, negative I, K, X, that is going to have to equal psi 2 at x equals 0. Okay, so let's set those equal to each other. So now that's C, E, kappa x plus d e to the negative kappa x, all right? And at x equals 0, these functions have to be equal to each other. So what happens? Well, you notice these are all e to the power x, right? And so e raised to the power 0 is just 1. So this is going to help us create one boundary condition. So in other words, wave function at region 1 has to equal the wave function at region 2. And when I plug in that value of x equals 0, look, all the e's become 1s. And so thus I get a very simple condition which says a plus b has to equal c plus d. There's my first equation that's going to be useful. Okay. All right, so then what about at the x equals L boundary, right? Well, we note that wave function 1 has to equal wave function 2 at x equals 0. And similarly, wave function 2 has to equal wave function 3 at x equals L. So now that becomes the following. So I'm going to say wave function number 2. So first, sorry, I'm going to box that off, and I'm going to call it a number 1. Okay. So now the second boundary we need to worry about here is region 2, which is going to be CE kappa x plus DE negative kappa x equals the region 3 solution, which is going to be A prime E to the IKX plus B prime E to the negative IKX. And of course, this is at x equals L. And so now when I substitute that value of L, I unfortunately don't eliminate all of these E's, but that's okay because it gives me another nice condition. That says CE to the kappa L plus DE to the negative kappa L has to equal A prime E to the IKL plus B prime E to the negative IKL. And I'm going to box off this equation, and I'm going to call this number 2. That's our second condition of normalization. Okay? So now, what about other conditions? Well, the slopes have to be continuous. Sorry, that's terrible. That says slopes have to be continuous. Okay? And specifically, the slopes have to be continuous at x equals 0 and x equals L. Okay? So now, what I want to do is, first let's do the x equals 0. And I want to take the first derivative of the region 1 wave functions. I want to take the first derivative of the region 2 wave functions. And then I want to set those equal to each other. Okay? So the first derivative of region 1, so let's do that. Okay? So taking the first derivative, and I'm only, because I know, well, excuse me, I'll just go through the full derivative. Okay? So we know that the derivative of A times EIKX is just going to be so that's going to be AIKEIKX, right? And then that term is going to be negative B IKE negative IKX. Okay, now I want to take the derivatives of this region 2. All right, so that's just going to be C times kappa E to the kappa X. And then now that's going to be minus D times kappa E to the negative kappa X. So we remember that we've defined that position to be x equals 0. And remember, e raised to the power of 0 equals 1. So now all of my e's, right, when I place in a value of 0, they're all going to go away. And now what I'm going to have is e I k minus b I k. And that's going to equal c times kappa minus d times kappa. And I'm going to call this one number 3. And I'm going to box this one off as well. There's our third and final condition. And then finally, the slopes must be continuous at x equals L. So I'm going to do the same process here, but now I'm taking the derivative of region 2 and region 3. So we already did the derivative of region 2. Let's just rewrite that. That's going to be c kappa E to the kappa X minus D kappa E to the negative kappa X. And so now we've got to set that equal to the first derivative of region 3, which is going to be A prime I k E I k x. I'm going to move this x equals L out of the way. And so now that's, minus, because there's the negative sign, right? And I take the derivative, and so the negative comes down. So now that's negative b prime I k e negative I k x. And because these derivatives have to be continuous at x equals L, I can't eliminate any of the exponentials. I just have to substitute x for L. So let's write that really quick. C kappa E kappa L minus D kappa E negative kappa L has to equal A prime I K E I K L minus B prime I K E negative I K L. I'm going to put a number 4 by that. That is our fourth condition. Let's see how we're doing here.